Thank you very much. We'll move on now to the second contribution, high TC superconducting copper oxides, given by Professor Tanaka, University of Tokyo.
Thank you. Okay. Thank you. I would like to talk about the result of studies of our group on high TC superconductors, which have been performed in these several months. First, I will show you a list of the materials of which we have studied in these 10 years. We tentatively classify the materials into 3 groups. Class 0 means barium, lead, bismuth O3, which is known as low carrier concentration superconductor and seems to be the prototype superconductor of the present high TC superconductors. The second, a series of materials of lanthanum barium to copper O4. The class 2 is lanthanide barium copper oxide, which are very high critical temperature beyond 90 degree Kelvin. In order to investigate new superconducting materials, the identification of the superconducting phase is the most important. To identify the superconducting phase, the 4 conditions must be satisfied, as is shown in the view graph. Crystal structure, Meissner effect, resistivity drops sharply, and the reproducibility of experimental results must be obtained. From November to early December of last year, we concentrated our effort in identification of the superconducting phase in lanthanum barium copper oxide, which was first suggested as a high TC superconductor by Dr. Bednoz and Miller. We succeeded to identify the superconducting phase and it is lanthanum barium 2 copper O4, having K2NiF4 type crystal structure. We succeeded to make samples of single phase of this type, and the temperature dependence of diamagnetic susceptibility and resistivity indicated that this material is a bulk superconductor and the critical temperature is about 30 degrees in Kelvin. We believe that these data were the most clear evidence of existence of high TC bulk superconductor beyond 30 degrees Kelvin at that time. Furthermore, we replaced barium to strontium and calcium and found that lanthanum strontium to copper O4 is a very good superconductor, TC of which reaches up to 38 degrees Kelvin. Furthermore, we investigate the physical properties of these K2NiF4 type superconductors of 40 degrees Kelvin. We think that these properties are very important since the K2NiF4 type structure is rather simple and it must be easier to understand the mechanism of high temperature superconductivity. We used a high quality sample. High quality means a large Meissner effect and very sharp drop of resistivity. Transition range is less than 1 degree Kelvin, as is shown in this graph. Time is not enough, so I only show you the result of our experiments. We measured mainly the we measure mainly the dependence of many physical quantities on the concentration of barium or strontium. Resistivity, Hall effect, carrier concentration increase with increasing doping. Zeebeck effect, next. plasma reflection. Omega p is almost 1.5 micron. Paramagnetic susceptibility. You see, this is x equals 0. The paramagnetic susceptibility increasing the with increasing the doping. And heat capacities. These data indicates a large density of states. Yes. This is ransom calcium kappa 4. The next one is this is ransom strontium kappa 4. And gamma BCS is quite large. And effect of high magnetic field. Temperature dependence of the conductivity and the high static magnetic field. HC2 estimated to be 60 Tesla. Okay, 6 Tesla. Okay. Summarizing these data, finally we make a tentative list of normal physical parameters and superconducting parameters. Next one. Yes, such like that. Furthermore, we replace ransom partly by rare earth elements. These results indicate that that the depression of critical temperature on the total temperature depend on the concentration, total spin of rare earth element. You see, this gadolinium is lowest critical temperature. So this means that this suggests the spin exchange interaction is conduction electron is effective on the critical temperature. Then I will talk about the result of yttrium barium kappa oxide, which was first made by Professor Chu. In Japan, however, Professor Hikami of University of Tokyo made yttrium barium kappa oxide quite independently and observed high TC of 85 degrees Kelvin in the middle of February of this year. We succeeded also to make yttrium barium kappa oxide of almost single phase. Almost you can see in this graph, the Meissner effect reaches up to 50%, and shielding effect signal reaches up to 150%. The rise of diamagnetic susceptibility, the diamagnetic signal is quite sharp at 94 degree Kelvin. The resistivity also drops fairly sharply at 94 degrees Kelvin. H1 is almost 100 Elsted at 5 degrees in Kelvin. Outer crystal structure, the pattern of X-ray spectra quite resembles that of lantern-2 strontium kappa 2O6. And then first we thought that it is S3B07 type. But later we found a line of a triple layer period of C. Then now we think that the crystal structure consists of triple layers. A model of this type of perovskite oxide was proposed by French chemist group, as shown in this graph. But the position of the oxygen ions cannot be determined by X-ray diffraction method. The correct identification of superconducting phase is a future problem. Now we proceed to new materials which were found by Japanese groups. We replace yttrium by other randomized elements such as yttrium, tritium, erbium, holmium, and diprotasium, and found that all of them showed high TC of 90 degree Kelvin. They have the same X-ray pattern as in yttrium, barium, copper oxide. I will show you some of the data as follows. Yttrium, erbium, diprotasium, and so on. It is very interesting. They have a magnetism at temperatures beyond critical temperature. So we can say that they are new type of high TC superconductors, and at the same time, they are new type of magnetic superconductors. It is surprising that the magnetic moments of these lanthanide elements do not affect the superconductivity at all. This fact may be related to the layer structure of these crystals. And, this may provide a basis to clear out the electronic structure of these high TC superconducting materials, as well as the mechanism of superconductivity. Thank you.
Thank you very much.